I'm currently on my last year of my PhD, and this is some of the work I've done there. I'll try to be brief since we have so little time, but luckily the previous speakers really explained that the robots will be a bigger part of our lives, both in the industry and at home. But there are some challenges with that, and maybe the biggest and obvious challenge, especially in the industry where you have robots that can lift 700 kilos and smash a human without even noticing, is the safety. Not only the safety, because we don't want the safety to compromise the productivity either. So there are some challenges there. There are a bunch of safety systems available today. Some of them are commercially available as well. You have the ABB Safe Move that detects the human, and you can have some predefined zones, and the robot will slow down or stop depending on where the human is. MRK Systema has some robots that detects if the humans are in contact with the robot, and the robot will stop. We also have Baxter, that's already been mentioned. Baxter is safe just because he's so weak. He can only lift 5 kilos, so he can't really do that much damage. And SME robots also have some systems. Now, there are also a lot of research on this. Lechevik have the research on, he's using danger fields, so he's trying to measure the current danger level in a human-robot collaboration. Kulkencroft has done some of the same in trying to indexing the danger. Mainprize and Berenson have tried to monitor the human and predict which task it's currently trying to solve, and then it knows the rest of this task, and it knows where the robot will be. There are some problems with these systems because they are so far from how we humans think about safety. We don't measure distances, and that's the only thing we do. We have this sense of risk in a way. In every little mundane task, if we're going to cross the road, we know there's a risk involved. When we get to a road, we can see how wide it is and how many cars there are, and we get this sense of, can we cross or not? We can't really quantify it, but we know, and we make a decision. Some has a higher level of risk acceptance than others, obviously, but now the government has added these small features to make some places safer to cross than others, like the zebra stripes. And then we know that we can go there and we can cross because it's a lower risk of an accident occurring at the zebra stripes rather than if we just run across the street. This isn't too easy to add to a robotics system, so we need to have some clear definitions of risk. Now, I'm working with a Norsok definition. I think it's a fairly common way of defining risk as a combination of the probability of an event and the consequence of that event. Now, the risk analysis is defined as the process of using this available information to identify the possible accidents and estimate the risk. If the risk is not acceptable, we add some risk-reducing measures, and we check if the risk is acceptable now. And we do this until the risk is acceptable. So a safety system is, in a way, it's just a series of risk-reducing measures, or RRMs. Now, if you look at these existing safety systems for human-robot systems, we see that most of them either focus on reducing the likelihood of an event, or they focus on reducing the consequence of the event. And they either focus on reducing this from the human side or from the robot side of the collaboration. We can reduce the likelihood of an impact between a human and a robot by using fences and barriers. That's the most well-known and most used way to do it today. Every robot cell has huge fences around them, So there's not really any collaboration. The most researched safety systems today is the obstacle avoidance-based approaches, where the robot can monitor the human, and if the human is too close, it will move out of the way. We can reduce the consequences of an impact, like with the Baxter. We can just make it really lightweight and weak, but that also compromises some type of productivity. There's very limited how much we can do with that kind of robot. Some more challenges with these systems is that they are only activated when we detect a possible accident. This is a bit tricky, but the fence safety systems, there's always a door lock. So if you open the door, the robot will stop. And your production stops as well. The other part is that the safety system is separated from, and it lies as a layer of higher priority than the process control. So it doesn't distinguish between a, call it a small danger and a huge danger. It does the same thing and it interrupts the process control. And if we're going to have productive human-robot collaboration, we can't really compromise the process control. We want the same level of safety, but without compromising on the process control. I was talking about these layers of risk-reducing measures earlier, and you want to start with a layer that have the least amount of other types of consequences. So the last thing you want to do is stop the entire production, but then you know everything is safe. So that's the last barrier of safety. Before that, it's normal to have a proximity-based emergency stop. So if you're close, the robot will, or the production cell will stop. The most researched level of risk-reducing measures is the reactive avoidance system, so that before there is or a potential collision, the robot will move out of the way, but it will also interrupt its task. What I want to do, and what we want to do in this research project, is to add another layer on top of all of this, which is a proactive avoidance system. What we hope is that the robot can make decisions about safety before you reach this situation that you have to avoid. A situation you have to avoid, if you reach this point, you're already too far or too close to a dangerous situation. Now, just the basic principles of this system. We try to quantify the risk associated with one single point in space. We try to estimate the likelihood that a human will be in this point based on a history of recorded data. So this could be in a work cell where we monitor the human, and after some time we have enough data so we can calculate the likelihood that a human will be there. We can also try to measure the consequence of different events. There is a very different consequence of a robot moving slowly into my arm rather than moving very fast into my head. Previously, there's not been distinguished about this, but to have a really productive collaboration, we believe that we have to distinguish between these things. And this will be part of the consequence analysis. Now, when we have done this for every point in space, it's fairly easy to construct a vector field upon this. We call this a risk field. Now, this map or this memory or knowledge for the robot can easily then be fed into a control system, both to, let's see, it was on my next slide. Yeah. We can use this to quantify the risk associated with a task for a robot. So before, we haven't really been able to measure or say if a robot operation is safe or not. So the current standard, I think it states that a robot must at all times be 50 centimeters away from the human. And that's the only measure, but there's a lot of difference between moving really fast, 50 centimeters beside the head, as I mentioned, or moving very slowly beside the arm at 50 centimeter distance. But with this field, we can now measure the entire risk in one task. The map can be directly fed to the robot, so we will always try to find the path that generates the lowest risk. And we can run this algorithm before it starts its task. And if it has a set of tasks it needs to complete, it can prioritize the safer tasks first and see if the risk changes for the later tasks. In this way, we combine the safety system and the process control so that they are no longer separated, but we use the safety to make decisions about the task. Now, I have a little pilot case I want to show to you guys. Now, it's a bit complicated. I won't spend too much time on it, but the green line represents a path programmed for the robot. Now, the robot wants to move along this green line from P1 to P2. The red here represents a path of a human limb. So there's something moving there all the time, but it's rotating, so it's not always in the robot's path. Now, the yellow line represents the deviation caused by a traditional obstacle avoidance approach. So the traditional way of thinking that if the robot is too close, move out of the way. But as you see, since the human is repeatedly returning to this path, the robot will sort of make these little weird jumps out of the way. And the human has actually to push the robot out of the way 4 times just for this little path. And that's not very comfortable to work alongside a robot that jumps along the way. But if we use the human motion to draw up this risk field, the robot will take this blue path and it will just do one smooth curve around the area where the human is currently working. So rather than trying to enter the area where the human is working many times just to discover that, oh, I can't be here, I have to move out of the way again, it will just move around the entire space. Now, if you measure the risk of these different tasks, the green one again represents the planned path. Now, note that the risk level, these are just arbitrary numbers, so you can only use them to compare with other tasks. It doesn't really mean anything alone, but we can look at the reduction. This is the last one. With the planned path and the yellow obstacle avoidance strategy, we see that it doesn't really help that much on the risk in the tasks. So the risk, as we measure it, isn't really reduced. Rather, with the blue risk field-based approach, the maximum risk is significantly lowered in the entire path. If you want to know more about this, we have a paper on it. You can note the DOI, or I'm sure it will be available elsewhere. Thank you.
I'm going to try to be brief with the question. So it's about the role of uncertainty in handling this kind of situation. If the robot is uncertain about the location, we can of course just scale up the uncertainty in the risk field. The problem might be, what if the robot is wrong about the shape of the space it's in, especially the topography of the space? Here we have a simple R3 situation, but in reality, organisms and robots will discover aspects of the reality around them that are going to be surprising.
Yeah, that's of course a very important issue, and with these predictions, so it's not meant to be replacing the other safety systems. We want this to be a layer above them, so that still, if it detects the human very close, it should still move out of the way. It should say, oh, you shouldn't be here now. this is my turn. Of course, it should then avoid it. And also based on how much data we have and how much specific routine it can see in the pattern of where the human is, it will have some of certainty how confident it is really about its decision. Yeah. And we can also use this so as we say, if the robot knows that it's not really confident about the risk, we can have it just to move slower, and that way also reducing the risk. So we can manipulate the speed.
What I'm getting at is there is a difference between uncertainty and ignorance. It's when the robot finds out that it's ignorant about some relevant factors, where you get a really interesting decision point.
Yeah.
Very brief.
Sorry?
A very brief question. To what extent is your work influenced by TA studies or by a critique of robotics?
I can admit that I learned about TA yesterday. So, not very much, but yeah.
No, but I would say that working with this type of topics, that these are elements that you should include precisely to make assessment of these technologies. You can't ignore them. That's why this cooperation with engineering related with robotics is so important. Because usually we can think about the use of robotics in our daily life, in different spheres of our daily life, as Ini has just presented. But ignoring this kind of methodologies can be dangerous in the sense that then we cannot understand really the implications of those systems. We can be fascinated about them, but without knowing in real life how far they can be applied, or what are the problems that can occur. And you just mentioned one, but there are also Simon mentioned at other times that we can collect several problems that should be included in these exercises for assessment of such technologies. We can.
Okay, just a quick question. So if you combine your processing system and then your safety system, does that mean if the processing system breaks, then the safety system is also broken? And that's sort of the sort of first principle of sort of normal accidents. It's a famous book in sociology of accidents by, I think it's Perlman or whatever his name is.
So,
Harris.
Yeah, I tried to explain this with the levels of the RRM. So obviously we still need the emergency stop button, which is not connected to the process control. But it would be nice with this added level, which is combined with the process control, so that we can try to avoid having to push the emergency stop button. As the first presenter mentioned, with these operators intervening 20 to 30 times a day, and that now that involves stopping the entire robot system. If you could just walk in there and knock this little piece into place, and not having to stop everything, that would be
But these
great.
situations are not necessarily inside the fence, but
Okay, yeah.
you must understand the whole. Yeah, it's not opening and closing.
Yeah, not all of them, but many, I guess, are
It's
inside
on the
as well.
preparation of.
Yeah.
I suppose so.
Yeah, of course, they don't stop at
Yeah, yeah.
Yeah, that sounded way too much.
But
For me, that's
without
not
these interventions, then
Yeah.
the robot would have problems to pick up
Yeah.
the pieces.
Yeah.
This is, yeah.